Good morning. Hope you're all doing well. As Pinar said, I'm Anahid Behrouzi, and I'm presenting on behalf of two of my recently graduated master's students, Tracy Doan and Jenna Williams. They were co-advised by a faculty colleague of mine at Cal Poly San Luis Obispo, Peter Larson. A portion of their master's project was focusing on how to model lightly reinforced concrete walls using PERFORM-3D, and so that's what I'll be walking you through today. The outline is that we're going to talk about the research motivation, the experimental test specimens that were used for calibration and validation of their modeling techniques, the preliminary modeling approach that they used, calibration, and the findings from their investigation. So what motivates this work is the performance of lightly reinforced concrete structural walls in the New Zealand 2010-2011 earthquakes. It was relatively poor. And what the concern is for this wall is not about the strength, but it is about the drift capacity and the fact that these perform in a non-ductile manner. Many of the walls that performed poorly were characterized by three main characteristics. They had low gravity loads, light steel reinforcement ratios, and no boundary elements. And unfortunately, a survey done by the ERI Concrete Coalition of Buildings in California indicate that we are dealing with many pre-1980s buildings that would have similar characteristics to the type of walls that we saw in New Zealand. The concern here isn't just with loss of structure that we see in these images, but also with the loss of community. So this is something very important to us. So we actually started at Cal Poly in the spring of 2019, doing a large-scale test of a lightly reinforced concrete wall in that the longitudinal and transverse reinforcement ratios were very low. There were no boundary elements in these walls in the traditional sense with any sort of confinement. This was similar to walls tested at the University of Auckland by Liu et al. And so these form kind of the baseline models that we are looking at to help us calibrate and validate the PERFORM-3D models. What you can see is in general, the hysteretic behavior of these walls are similar. In terms of damage progression, what we see is these large but very few flexural cracks that form towards the base of the wall and have major strain concentrations at those locations, generally with limited distributed cracking, although in walls C2 and C3, you do see more distributed cracking because they are loaded with a moment gradient so that they can model a higher shear span ratio for the wall. So the students that I was working with, they wanted to start off with wall C1. It has regular 2-cycle set displacement-based loading protocol, and it also did not have the moment gradient that we see in wall C2 and C3. So that is the baseline that we are starting with. In terms of the PERFORM-3D parametric study, why did we choose that software? It is utilized in industry to create detailed models of shear walls to capture the nonlinear material behavior across fiber cross sections. And there is a really great document that's been prepared by Lowe's et al. That does talk about how to model reinforced concrete shear walls with this software. But we were specifically looking at lightly reinforced concrete walls and wanted to investigate how those recommendations performed in that scenario. So in particular, the students were looking at concrete models. We're going to use an unconfined model because we do not have boundary elements with confinement. They also wanted to investigate two different rebar models. So industry members have different approaches for this. There was a no strength loss model suggested by Lowe's et al. And then per our industry advisor, they suggested a strength loss model that they tend to use when doing these type of wall modeling. And then also investigating meshing both in the horizontal and the vertical direction. So those are the parameters that we will start with. In terms of the nonlinear concrete model, we're looking on the left at just a compression only model for Mander. And then the second version that was investigated had compression using the Mander model and tension with Huang and Riscala. One of the shortcomings you will notice, because the gray line is the constitutive model and the red line indicates what was actually input in PERFORM-3D, is that PERFORM-3D only allows you to define about 5 points on the compression and the tension sides each. And so The students did define the peak strain, du, at the ultimate stress, where the strain is at the intersection of the initial tangent and plastic unloading. dr is the point of strength loss that Mander defines as 95% of the strain at which cover concrete is considered to have completely spalled and ceases to carry any load. And then we have the final strain of the material as dx. So on the nonlinear steel side of things, the left-hand side, you see the model that is proposed by our industry collaborator from Degenkolb, Los Angeles office. And that is that for the du on the compression side of things, that should be aligned with the concrete strain capacity, whereas on the tension side, it's aligned with the steel capacity. Then we move on to the dr, which the stresses that are correlated with strength loss, those are determined per PERFORM-3D's minimum allowable value of dl being 1% higher than the ultimate strain du, and dr being 95% of the final strain dx. You can see that the final strains for that rebar strength loss model are equal in both directions at 0.1 and negative 0.1. That was also a recommendation from our industry collaborator. The rebar no strength loss model that you see on the right is consistent with the recommendations from Lowe's et al. As the name suggests, there is no drop in strength with this particular model, and we were interested in how these two would compare and which one might perform better up against the experimental data. In terms of horizontal meshing, you can see the cross-section for the Lu C1 wall that we're focusing on the left, and you can see that in PERFORM-3D, it's possible to break up the cross-section of a wall geometry to lump rows of steel into a steel fiber and place it within a concrete fiber. And the students were able to do that with 1, 3, and 7 horizontal meshes. They also explored 1, 3, and 7 vertical meshes for a total of 9 variations that were investigated. And so looking at all of these parameters together, the horizontal vertical meshing, whether or not there was concrete tension represented in the concrete model and whether rebar strength loss was considered in the rebar model, that led to 36 wall models in their parametric study as shown here. So the first thing they wanted to look at was the mesh variation and which led to the most accurate results. The gray dotted lines you see in each of the figure represent the experimental data, and then the titles across the top give an indication as to the vertical meshing, and the colors that you see in the key give an indication to the horizontal meshing. So out of all of these, hopefully we can tell quite clearly that the purple line in that third plot, which is a 7x7 mesh, was the most accurate, and this has about an aspect ratio of 2:1. So that's what they were using. The next thing they investigated was the rebar models. These plots right here show the 7x7 models that had no strength loss, and what you can see is globally the strength just is maintained on and on to very large drifts, which is not realistic, so these two models were rejected. Now moving on to the 7x7 mesh models that had strength loss, we see model 33 and model 35, but it looks like the initial stiffness and the peak strength of model 33 captures the performance a bit better, so that was the model that the students proceeded with for their pushover. They had a couple of other parameters they wanted to investigate, one of them being modifying the value for strength loss at dx. And so the original pushover you can see in this red dotted line, and the strength loss at dx is yellow. This was not applicable because we only see a difference at 3% and above in terms of drift, and that's an unreasonably large deformation that industry practitioners would not really be interested in. And so the recommendation here is that you do not need to consider a modification on the total strength loss at x dx. Then they also investigated the effects of the P delta for the pushover. The concern there was perhaps as you apply a gravity load to a laterally displaced wall, there would be some effect that needs to be captured. But what we're observing here is that as the drifts get larger, the drop in strength becomes more significant and does not align as well with the experimental data. So at this point, the students decided to ignore the effects of P delta. They also did a little bit more kind of adjustment with the strength loss rebar model with respect to the wall degradation by changing the rebar's post-peak negative stiffness slope by modifying the DR value in PERFORM-3D. So if you look at the small plot on the right, you can see the material model and where DR is defined. That is associated with the red line on the pushover, where they were using 0.07 for the original DR. And they found that if they modified that DR value to 0.1, they got a better match in terms of how the strength loss affects the global response of the wall. So that's what they continued on with. But we're not just interested in the overall kind of initial stiffness and the maximum strength and where we have our final drift. We also are very interested in, do these models give an accurate prediction of material behavior limits and ASCE 41 strain and rotation limits, and also the wall final failure. So what you can see here is the experimental pushover in gray and the PERFORM-3D model in black. And these markers indicate, for example, that concrete cracking and concrete crushing are very well predicted in terms of the drift. And in terms of rebar buckling and rebar fracture, it's a bit overestimated in terms of drift of when those will occur. When we're looking at the ASCE limit states, we see that we have concrete compression at 1.25% and rebar tension at 1.6%, and that we see relatively, we have some conservatism in the immediate occupancy, life safety, and collapse prevention states as compared to the experiment. So then from the pushover model, we move on to the cyclic models in PERFORM-3D. These are more time consuming to perform, but can give us some useful information about energy dissipation and things like that. So again, model 33 was the forerunner of the cyclic models in terms of its ability to capture this the strength, initial stiffness, and kind of this degradation of strength as we go through the cyclic behavior. There was a bit of an issue that the students identified, and that was with this kind of spike that's on the first loop that they discovered was happening because they used the material modulus of rupture test value from Liu et al., when really it seems more appropriate to use some percentage of that. And so they were able to eliminate that kind of false spike that was showing up in the model by using 20% of the modulus of rupture value. So then you can see kind of their resolved model on the right once they've dealt with that initial spike. They also investigated energy dissipation factors. So you can see that there is the energy dissipation factors associated with PERFORM-3D, and that is defined by Y, U, L, R, and X. And originally from the recommendations from Lowe's et al., the Y and U are supposed to be set at 0.4 and the R and X at 0.1. Those are the recommendations. Just to give you a sense of what these values even mean, if you're putting in a value of 1, that means you have max energy dissipation. You still have 100% of the energy left in the system, and 0 means there's no energy left to dissipate. And you can actually set these values for your concrete material and your steel material separately. And so the students ran another model where they modified the YULRX to 0.75, so they increased the remaining energy dissipation potential of the steel model so that it would better account for strain hardening in the steel. And when you look between the two different plots, you see that the loops become much fuller for the plot where you allow for strain hardening, and so it better captures the overall response of the C1 wall test. They also examine stiffness factors. So there's various ways that you can specify the unloading and reloading stiffness to control energy degradation. They looked at the options of -1, 0, and +1, and what they ended up with as the best match is the +1 value in terms of capturing that 2.5% kind of return on the loop. So if you're looking at that specific return, you'll see that that does a much better job. So the last thing we're looking at is the strength loss interaction for the rebar model. Initially, they were using an assumption that strength loss in one direction led to no strength loss in the other direction. And in contrast, the right plot that we're looking at on the slide shows strength loss in one direction equal to the strength loss in the other direction. The PERFORM-3D manual suggests that it might be a useful assumption if, for example, a component was diffraction and tension, that you would want some strength loss in compression as well. But the students found that actually using a strength loss interaction factor of 0 was more appropriate because the steel model that they were already using was asymmetric. So that would capture these type of effects rather than using a strength loss interaction factor that was anything other than 0. Again, we're looking specifically at the return on the final 2.5% loop as an indicator of capturing the strength loss interaction appropriately. So then we look at the strain limit verification. Just as a point, it is much more complex to make a cyclic model in PERFORM-3D than doing a pushover. So the students wanted to see if it was reasonable for a person to just go ahead with a pushover and not have to go through the whole process of doing cyclic analysis. And so what they found is that the only limit state that seemed to have any inaccuracy between the two modeling approaches was concrete cracking, but otherwise in terms of concrete compression, rebar tension, rebar buckling, concrete crushing, and all of these rotational limit states from ASCE 41, they are identical. So if those are the parameters that you're looking at, then a pushover would do you just as well as your cyclic analysis. So here's the results you see from the pushover in red, the experiment in dotted gray, and the PERFORM-3D cyclic analysis in black. They also wanted to see how this did against the 3 other walls that I showed you, W1 being the one tested at Cal Poly. So you can see the results with respect to the pushover with the limit states and the cyclic. The 2 other walls that we spoke about from Auckland that have the additional moment gradient to model a higher shear span ratio. You can see again, pushover slightly underestimates strength and it's showing higher drifts, but then when you look at the cyclic results, these do quite well. The strength is still underpredicted for C2, so I think that's a point we'll have to explore a little further, just looking at how to capture the moment gradient more accurately. And here are the final recommendations that the students came up with in terms of element mesh size, concrete material model, rebar model. The other parameters they investigated strength loss at X, P delta, and then some recommendations on the cyclic load analysis side of things with respect to energy dissipation, unloading, reloading, stiffness, and strength loss. So that's a summary of all of those items. And if you want to learn more about all of this work, the report is available on our Cal Poly Digital Commons under this title. And also, one of the students made a very comprehensive video tutorial on how to model reinforced concrete walls in PERFORM-3D. It's about 50 minutes long, I want to say, and has had several hundred views since its posting. And you can find that under this title and her account name, Jenna Williams. Just want to acknowledge all the folks that supported us in testing the large-scale wall in spring of 2019 and that provided funding for that. And I don't think that we have any questions, but you can always email us at calpolyrcwalls@gmail.com, and that is the specific email for our project. Thank you so much for your attention, and I'll turn it back over to our moderators.